Okay, and we move on now to chapter 15, which is called Optimizing, it's called spelling, Optimizing Complex Networks, graph theory. Essentially, it's graph theory. That's the name of the branch of mathematics. And what will we be doing with this graph theory? We will be optimizing complex networks. Okay, well, first of all, let's start with a definition of what exactly a graph is. Definition. A graph is defined as a set of vertices and a set of edges. So you provide two sets. The first set will be the set of vertices. The second set is the set of edges. Is there any connection between them? Yes. A vertex, which is a singular of vertices, a vertex represents an object. Now, this is nice for high school level graph theory, so that you have a concrete picture in your mind of what's going on, but just know that in a more advanced level, it's much more abstract, and a vertex does not have to represent an object. But for now, a vertex represents an object, period, and an edge joins, not joints, but joins two vertices. So it looks or sounds somewhat complicated, but as we go through them, we're going to see that it's actually not. In fact, I'll just draw a graph right now. So here's an example of a graph. It is given by the following table. This is called an adjacency table. This is an adjacency. How do you spell it? Adjacency. There's an E in there. ADJACENCY, adjacency table. There we go. And essentially what we do for an adjacency table is we list the vertices, A, B, C, and D. We list them both as rows and columns. And then what we do is we assign a number to each connection between A, B, C, and D and A, B, C, and D. And the number tells us how many edges join them. So here's an example of an adjacency table. So let me fill it in. This is on page 692. So here's an adjacency table. And what we're going to do is we're going to make a picture of a graph. We're going to make a graph to represent this. So we have point A, vertex A, which we see has one connection to vertex B and also one connection to vertex C. So this takes care of the first row. A goes to B and goes to C. The second row, B connects to A. Well, we already have that, so I don't have to draw it again. And B also connects to C, so we'll throw that in as well. C connects to A, C connects to B, and C also connects to D, so we'll throw in another vertex D and have a connection there. And then D connects to C. So this is the graph, or a graph, represented by the adjacency table. There's infinitely many pictures that I can draw. If I want, I can have A, B, C, and D all in a line. A goes to B, A also goes to C, B goes to A and C, C goes to A, B, and D. See, okay, this is another example. It's the same graph. It's the same connection, the same adjacency matrix. As far as we're concerned, from a graph theory perspective, those are the same. We don't have to draw, they don't always look the same. What matters are the vertices, A, B, C, D, the edges, A, B, A, C, B, C, and C, D, and that's it. Vertices and edges, that's a graph. Look at the original definition. Vertices and edges, that's all we have to worry about. Now, let's immediately throw in a slightly more sophisticated definition. A walk is any sequence of vertices pass through when moving along the edges, of the graph. So I'm going for a walk. What's a walk? You start at some vertex and then you move along the graph in whatever direction you want. Vertex, edge, vertex, edge, vertex, edge, vertex, edge, ending at some vertex, any sequence. So as an example, using the same graph that we had a minute ago, it says write down 2 possible walks from A to D. So one walk from A to D would be A, C, D. That is the shortest walk. I can also go A, B, C, D. Those are the 2 most obvious, but there's actually infinitely many walks from A to D. I can do A, C, A, C, A, C, D. That's a valid walk from A to D. Kind of silly. Maybe you left. Oh, I forgot something at home. You went back. Then you went. Oh, I forgot something else at home. I mean, you can come up with any scenario. But this is, there's multiple. I mean, you know, A, B, C, A, C, B, C, D. You know, there's infinitely many different walks from A to D. Okay, let's do another example. Okay, so let's start with an adjacency table. This one has 5 vertices, A, B, C, D, and E. A, B, C, D, and E. So let's make the adjacency table. And by the way, notice about the adjacency table above, and this one as well, that it is symmetric in the sense that if you look at the numbers, those match, those match, those match, and those match, because A to B and B to A, it's the same connection, A to C, C to A, B to C, C to B, C to D, D to C, right? You're always gonna have this symmetry along that diagonal, along the main diagonal. It's gotta be a perfect mirror image, assuming it's a regular good old-fashioned graph where you can go along an edge in either direction. Later in this section, we're gonna have what are called directed graphs or digraphs, where maybe you can go A to B, but you can't go B to A. And in that case, the direction matters, but we're not there yet. So for now, here is our adjacency table. Actually, I take that back. And this is not an adjacency table. It's a little different. This is going to be a weight table. And it's very important when you do problems that you know what kind of table you're dealing with, whether it's an adjacency table or a weight table. So in this case, I'm going to put in the weights. 4, 5, 7, 5, 3, 6, 2, 3, 6, 6, 2. Notice again, by the way, that if I draw along the main diagonal, I have perfect symmetry. But this is a weighted graph, okay? And the table shows costs in dollars of traveling by bus between towns. So let's make a weighted graph. Here's point A. Now A can go to B, and it's going to cost 4 units, in this case dollars, $4. A can also go to C, and that's going to cost $7. Or A can go to D, and that's going to cost $6. So I have my upper line, I have my 3 weights on my graph. We already have B to A, so we can go B to C. Oh, look at that. I'm going to go around this way, so I don't have to go and cross a line. B to C has a weight of 5. And then C to D has a weight of 3. And then D to E, oh, that's a new one. So we'll put an E, has a weight of, oh, wait a second. Not D to E, although D also connects to E, so I might as well throw it in there. DD is 2, but C to E was 6. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. I have all of my weights. So what kind of questions might you ask in regards to a weighted graph that combines what we just did a few minutes ago in terms of walks? It's something along the lines of, what is the least weight walk from A to E, for example? In this case, it's pretty, well, is it straightforward? Actually, yeah, it is. A to E. Well, if we go A, D, E, that is a total weight of 8. If we go A, C, D, E, that's got a total weight of 12. If we go A, C, E, that's got a weight of 13. So it looks like ADE is the walk of least weight. And these are the types of questions that we're going to ask ourselves as we progress through this chapter. So for now, let's go ahead and do the exercises. Paying very close attention as we do them as to whether or not it's an adjacency table or a weighted table. So this is exercise 15A. Number 1. It says state which of the graphs represent the information given in the table. Okay, so there's a table here. I'm going to first make the table. It's got 6 vertices, A, B, C, D, E, and F. A, B, C, D, E, and F. And from the looks of it, based upon the multiple choice possibilities and the numbers, it is an adjacency table, not a weighted table. And the weights are 1, 1, 1, 1. Not the weights, I'm sorry, the numbers. This the placements of the numbers. 1, 1, 1, 1, 1, 1, 1, up there, 1, and 1. So again, let's draw a line directly through the main diagonal. Symmetry, symmetry, symmetry. Yep, we got good symmetry. So we have some options here, and the question is which of these are represented by this adjacency table. So the first one is A, B, C, D, which also connects to A, and has an EF connection like that. So the question is this represented by the table? So pause it and do it yourself, as always. So let's take a look. According to the table, A connects to B and D, which this does. And B connects to C and F. I mean, besides already A. So the new ones, we're focusing our attention on those because everything to the bottom of the line is redundant. So we just got to check top. So B goes to C and F and A. I guess we should be careful. B goes to A, C, and F, which it does. C goes to B and D, which it does. D goes to A, C, and E, which it does. E goes to D and F, which it does. And F goes to B and E, which it does. So that is correct. How about this one? We have B, F, E, D, C to B with an A to D inside. So pause it as always, check your work. Let's see. According to the graph, A connects to B and D, which this does. B goes to A, C, and F, which this does. C goes to B and D, which this does. D goes to A, C, and E, which this does. E goes to D and F, which this does. And F goes to B and E, which this does. So again, we have a good one. C has A, B, C, F, E, D to A, and E also goes to A. So as always, pause it and check. So let's see, A goes to B and D, which is, this one has an additional connection, AE. So first line already tells me that this does not work. There should be no edge connecting A and E, so that's out. D has a shape like this: A, B, C, D, E, and F. So go ahead and pause. So let's take a look. A goes to B and D, correct. B goes to A, C, and F, which it does. C goes to B and D, which it does. D goes to A, C, and E, which it does. E goes to D and F, which it does. F goes to B and E, which it does. So that's another one that's good. And then finally, the last one, E, D, C, B. Oops, let's put the B somewhere else. Put it here so I can make this F, E, wrap around to D, and we get an A in here as well. All right, so pause that one and confirm. So let's take a look. A to B and D, yes. B to A, C, and F, yes. C to B and D, yes. D to A, C, and E, yes. E to D and F, yes. And F to B and E, yes. So 4 out of 5. Notice that they look very different, but they are all the same graph, even though we wrote them differently on the page. What matters is the vertices and the edges. Question 2. Draw a table to represent the number of direct connections between the vertices in the graph below. Okay, so here we're going from graph and we're making an adjacency table. So we have A, B, C, which also connects to B, D, which also connects to C, and E. So let's go ahead, pause it, and make that adjacency table. So this is a 5 vertex table, A, B, C, D, and E. A, B, C, D, and E. So what do we have? A goes to B, to C, and to D. B only goes to A and C. C goes to A, B, and D. D goes to A, C, and E. and E just goes to D. You can always check to see if we have the symmetry that we want it to have, and those numbers do look aligned, so that's good. B, we have P, Q, and R as 3 vertices on what looks to be a circle. And then Q is also on another circle. Oops. Q also looks at another circle to point S and point T. And S and T have their own little connection there. Okay, so let's go ahead, please, and make the adjacency table for this graph. P, Q, R, S, T, P, Q, R, S, T. So P goes to Q and R. Q goes to P, to R, to S, and to T. R goes to P and Q. S goes to Q and T. Oh, goes to T twice. And T goes to Q and goes to S twice. So again, we have good symmetry. Notice for the first time, we have non-ones in my table. Okay, question number 3. Draw the weighted graphs represented by the following tables. Okay, so this is not an adjacency table because these numbers are big. I would not want to draw that many edges. We have 5, A, B, C, D, and E. A, B, C, D, and E. We have 15, 12, 10, 15, 13, 9, 12, 12, 10, 13, 16, 9, 12, 16. You might have noticed I'm not putting the grid in, and that's only because I'm lazy and it takes too much time. But if you do not write neatly, or there's any chance of screwing it up, I would recommend writing those, making that grid. So let's do the graph. Here's A. A goes to B with a weight of 15. A also goes to C with a weight of 12. And A goes to D with a weight of 10. Here, I'm going to make this so I only have to worry about the top right. B, in addition, goes to D with a weight of 13. And B also goes to E with a weight of 9. C also goes to E with a weight of 12. And D also goes to E with a weight of 16. So that is the, or A graph, a weighted graph that is represented by the weights given in the table. Here's another one, also 5 by 5. A, B, C, D, E. A, B, C, D, and E. We have 6, 10, 6, 7, 10, 7, 5, 5. So let's go ahead and make this one. So we have A, which connects to B with a weight of 6 and also connects to C with a weight of 10. B connects to C with a weight of 7. And then we have D and E, which connect to each other with a weight of 5. Notice how this graph is not one piece, but rather it's separate in the language of what's coming on the next page. we would call this a non-connected graph. This graph is not connected. It's not one piece. All right, question number 4. Draw weighted graphs represented by the tables below. So now this one is a 4x4, 4 vertices, but you'll notice something different between this and everything we've done so far is that this one is not symmetric. These are weights, not adjacencies. So what this means is as follows, that while there's an AB connection in the first row, there's no BA connection in the second row. So we have to be very clear on where we're starting and where we're ending. So it says each table is read from row to column. So the weight of the edge from A to B is 10. So from to is going to be the convention that we use in this book. So let's take a look at what we have here. Here's point A, and we can go to point B. I'm going to put a little arrow from A to B with a weight of 10. A also goes to point D. Here's an arrow with a weight of 7. B will go to point C with a weight of 8. C will go to point B also with a weight of 8. C will go to D with a weight of 12. So those arrows tell me, very importantly, which direction I'm going. The BC connection, you'll notice it's the same in both directions. I guess in theory, if you want to leave out the arrows to indicate that it's either way, that would be fine for your own work, but the person who is reading your work might not know what you mean, and therefore it's recommended to do it this way, where we have one arrow from B to C and a completely different arrow from C to B. Let's do another one. B, here's another 4x4. A, B, C, D, A, B, C, D. These are weights again. 10, 10, 6, 7, 8, 11. So we have A, and there's an arrow from A to B. It's worth 10. And B back to A is also 10. Meanwhile, B also goes to C with a weight of 6. And C goes back to B, but this one's a weight of 7. C also goes to D with a weight of 8. And D goes to A with a weight of 11. So we just represented weighted directed graphs where the direction matters. Let's move on now to question number 5. It says draw unweighted graphs to represent the table below. And this is again a directed graph because we don't have symmetry, which means the direction matters. It's an adjacency table, but it's an adjacency table with direction. So A, B, C, D, we have 1, 1, 1, 1, 1, 1. So that means here's A. A goes to B. A also goes to D. B goes back to A. C goes to B. C goes to D. And D goes back to C. So that would be an unweighted directed graph. We have no weights, but we have directions. A and B and C and D, that part, yes, you go back and forth, but the AD-BC connections, those are certainly one-sided. And then here's another one. We got 4 points, A, B, C, and D, A, B, C, and D, 4 vertices. We have 1, 1, 1, 1, 1, 1, and 1. So let's see, we got A can go to B, A can go to C, and A can go to D. Meanwhile, B can go to C, and C can go to B. C can also go to D, and D can also go to C. This is probably not the cleanest graph. I'm sure somebody could make one that's easier to read. You also want to be careful, like this A to D connection. Now that I look at it, it's like, which direction is that going exactly? So, you know, even that's not that good. Maybe just even without the base. Although the point is, however you decide to do it, just make sure that it's easily legible. And if it's not, which does happen sometimes, especially if you're going quick, just redo it. Okay, question number 6, the last question in exercise A. Now, this is a big table, and I'm not going to copy it. So this one you basically can only do if you have it in front of you. Otherwise, otherwise I'm not doing it. So a salesman needs to travel from Sheffield, I'm going to call it SH because it's the only city that starts SH, to Manchester. I'm going to call that M since that's the only one that begins with the letter M, to Nottingham, which I'm going to write N-O-T, and then back to Sheffield. So this is the path that the salesman needs to travel. A route finder algorithm has been programmed with all the data in the table below, showing distances in miles between the major cities in England. So if you look at this table, there's every pair of cities in England, or these major cities in England, like York and Birmingham, for example. The top left is 129 miles from York to Birmingham, and of course that's also from Birmingham to York because distance is symmetric. Unfortunately, the information on the distance from Manchester to Nottingham has not been included. So somehow that little square in the center of the table is absent. A. Write down the distances from Sheffield to Manchester. Okay, no problem. Sheffield to Manchester. Let's just find Sheffield and Manchester. Oh, that's 38 miles. And then from Nottingham, I'm going to actually put this up here, 38. And then, and from Nottingham to Sheffield. So here's Nottingham. No, Sheffield, Nottingham is 39. Okay. So that's part A. I'm going to move that up here. Okay. In trying to give an estimate for the shortest distance, the algorithm will find, sorry, I'm trying it again. Words, English. In trying to give an estimate for the shortest distance, the algorithm will find the shortest distance from Manchester to Nottingham via one other town. Okay. In other words, it has no idea what this is. So the best it can do is say, okay, suppose we include one extra city in the middle. Let's go through every possibility of Manchester to blank to Nottingham and list them all. Okay, so again, in trying to give an estimate for the shortest distance, the algorithm will find the shortest distance from Manchester to Nottingham via one other town. To do this efficiently, it needs to reduce the table as much as possible. B, explain why all those towns further than 77 miles from Manchester can be excluded from the search. Why is it that every town that's further than 77 miles from Manchester can be excluded from the search? Take a second, come up with a reason, pause, and then we'll come back. Okay. All right. So hopefully you've done that. So if you think about it, we know that Manchester to Sheffield. Well, let me think how to explain this the best way. All right. So let's think about it. If I go Manchester to Sheffield to Nottingham, we know Manchester to Sheffield is 38 miles, and Sheffield to Nottingham is 39 miles. Those are the two things from part A, which means which as a result, it means Manchester directly to Nottingham. This must be less than or equal to 77 miles. If Manchester, Sheffield, Nottingham are all in one line physically along the map of England, then 38 plus 39 is 77. If not, if it's off kilter somehow, then it will necessarily be less than 77, the shortest distance. It's called the triangle inequality in mathematics. That the shortest distance between 2 points being a straight line, if you go through any other route, the third side of the triangle, this side, must be less than or equal to the sum, or less than specifically, the sum of those two sides. The triangle inequality is extremely important in mathematics. Oops, don't say it, that was the wrong word. In mathematics, it's there's a whole branch of mathematics called metric space theory, which deals with structures that obey the triangle inequality. Very, very important. Anyways, so we know that the algorithm that we're working with, this computer program, does not have to worry about any town more than 77 miles from Manchester, because the distance from Manchester to Nottingham must be less than or equal to 77. So now it says, draw a graph showing all remaining routes from Manchester to Nottingham, which go via one other town. Okay, so we have a list of towns. Manchester to York is 65, and then York to Nottingham is 80. Too much. Okay. Manchester to Southampton is 208, already too much. Manchester to Sheffield is 38. Oh, we already know that one, of course, so I'm not going to write it. We already have that one. Manchester to Portsmouth, 222, too much. Manchester to Oxford, 144, too much. Manchester to Nottingham, I don't know it. Manchester to Norwich, 185, too much. Manchester to Newcastle, 131, too much. Manchester to Birmingham, I'm going to call it BI for Birmingham, is 81. And then Birmingham to Nottingham, I don't even care. It's, oh, wait, I don't even write. 81 is too much. My cap is 77. Manchester to London, 111. Manchester to Liverpool, 90. Manchester to Leeds, 110. I'm looking at the wrong row. Take all that back. Manchester to Bristol, 162. Manchester to Derby, 59. So here's D for Derby, 59. And then Derby to Nottingham, 16. Ooh. Manchester to Exeter, 238, too much. Manchester to Leeds, I'm going to call that LE, 41. Leeds to Nottingham, where are you? Leeds to Nottingham. 70. Too much. Oh, Manchester to Liverpool is 34. Liverpool to Nottingham, 99. And then Manchester to London is 184. So, D, hence, state an estimate for the shortest distance the sailorman must travel to visit the two towns and return to Sheffield. So, the shortest route from Manchester to Nottingham, we know that we can go directly on top, that's 77 miles, but it looks like if we go through Derby, 59 plus 16 is 75. That means I can do it in less than or equal to 75, which means 38 was the original Sheffield to Manchester, plus 59 plus 16, plus the remaining 39. That gives me 77 plus 75 was what, 140 something? I don't know, I'm too tired. 77 plus 70, 38 plus 59 plus 16 plus 39 gives me a maximum of 152 miles. Of course, like the chapter on matrices, you don't really need a graph theory to do this. You could have done it without graph theory. So like that chapter, we're going to see that as we progress through the chapter, uses of graphs are going to become more and more important versus just, oh yeah, I can use a graph for that, even though I don't really need it. Okay, so let's continue with definition alluded to earlier. In a connected graph, it is possible to construct a walk between any two vertices. And so if you go back up to this one, way up here, okay, it was not far. Here we go. This is not a connected graph because there's no vertex edge sequence, vertex edge, and so on, which can get you from A to D, for example. A, B, and C are, you can walk amongst them all you want, but you can't make the jump to D or E. It is not a connected graph. A subgraph of a graph consists entirely of vertices and edges that are in the original graph. So if you have a graph, a subgraph is obtained by just removing any edges or vertices you want, such that what you're left with still satisfies the properties of being a graph. In other words, if you have two vertices and an edge, you can't remove the vertices and keep the edge because the edge needs to connect the vertices. But if I have my original graph is this, that's my graph, we'll call it graph G, then this graph H would be a subgraph of the original graph because everything in H is in G. Yeah, actually that's it. Everything in H is in G. Technically, even this is a subgraph because everything is in H is in G. It's just a silly subgraph. You're basically saying the original graph is a subgraph of itself. Technically, it's true. It's just very boring. Okay, subgraphs are really only exciting when you actually remove something and then start asking about properties with what you have, okay? Now, another definition. In a directed graph, all edges are assigned a specific direction. All edges are assigned a specific direction. So you can't have one edge with an arrow this way and an arrow this way to indicate you're going both ways. You have to have two different edges. One this way, one this way. A directed graph is connected. So now the word connected means that you can make a walk between any two vertices. But if it's a directed graph, you got to be careful because sometimes you can walk in one direction but not the other, which might play a role. So in a directed graph is connected if a walk can be constructed, in at least one direction between any two vertices. So we say the directed graph is connected if you can walk in at least one direction between any two vertices. Maybe not back and forth, but at least one direction between any two vertices. A directed graph is strongly connected if it is possible, and hopefully you already see where this is going, if it is possible to construct a walk in either direction between any two vertices. Now that we have this definition, strongly connected, some people go back and call the original one weakly connected. We'll put it in parentheses to indicate that you can say it or not say it, and it means the same thing. Okay, so you don't have this concept in a regular graph, because if you can go one way, you can always go the other way because there's no directions associated with any edges. So this concept of strongly connected and weakly connected only holds for directed graphs. Another definition, the degree of a vertex is the number of edges with that vertex as an endpoint. An even vertex has even degree. An odd vertex has odd degree. Now, what about a directed graph? Because in a directed graph, what if I have an arrow going in and an arrow going out? Do I want to count both of them for that vertex, or do I want to differentiate between them somehow? And the answer is I can, with our final definition of the section. The in degree of a vertex in a directed graph is the number of edges, with that vertex as an endpoint. In other words, if we're coming into that vertex is an endpoint. The out degree the out degree of a vertex in a directed graph is the number of edges with that vertex as a starting point. So I think most of these definitions, if not all of them, are very intuitive. So we're going to go directly now into exercise 15B and do some problems associated with all of these definitions. So question number 1. A group of people share several attributes which can be shown in a graph with the 5 people as the vertices. The edges represent the connections between them. For the following connections, discuss whether it will be best to draw a directed or an undirected graph. So A, what is an edge equal to here? An edge equals lives on same block. Would that better be made with a non-directed, a regular graph, or a directed graph? So this should be a non-directed graph, a good old regular graph, because if A lives in the same block as B, B automatically lives in the same block as A. There's automatically a symmetry, where if A is connected to B, B must be connected to A. B, an edge equals is the sister of. Is the sister of. Is that better for directed or non-directed? And the answer to this will be directed, because if A is the sister of B, that does not mean that B is a sister of A. Okay, my sister is my sister, but I'm not her sister, I'm her brother. 2 different things. C, what is an edge equal to? Is a friend of. So that better for directed or non-directed? So this one, I guess it depends on your definition of friends, because sometimes one person feels that they're a friend of someone else, but it's not reciprocated. So it's a tough one to answer, because if friendship is reciprocated, then it's, I would say, non-directed. And if friendship is not reciprocated, if you can be a friend of someone else and not vice versa, then they will be directed. And D, an edge equals is a follower on Twitter of. On Twitter of. So which should this one be? And the answer is directed, because just because I'm a follower of you does not mean you are a follower of me. So I think the only questionable one there is C, because depends on, from a sociological perspective, of what a friend is. All right, question 2, part A. Draw a table to show the information contained in each of the following directed graphs. Okay, so what do we have here? We have a circle. And on the circle, we have point A here, and vertex B there, and C down here on the left, and D over there on the right. And we have an arrow this way, an arrow this way, an arrow this way. We also have another connection here between A and B with an arrow going this way, and another connection between C and D. So this original one is that way, and this one is that way. All right, so we want to draw a table for this one. A, B, C, D, 4 vertices, A, B, C, and D, A, B, C, and D. So let's see, A goes to B 1 time. Okay. B goes to A one time. B also goes to D one time. C goes to A one time. C goes to D one time. And D goes to C one time. All right, that seems like it to me. Number B, letter B, whatever. So here, it's like a diamond. And with another little path there. This is B, this is A, this is C, this is D, and we got some weights here. Not only do we have directions, but we have weights. So I'm drawing them right now. 9, 5. Okay, so let's draw a weighted table. A, B, C, D, A, B, C, and D. A doesn't go anywhere. B can go to A with a weight of 8. Okay. C can go to A with a weight of 9. C can also go to D with a weight of 4. D can go to B with a weight of 7, and D can go to C with a weight of 5. All right. So actually, this wasn't B. This was A part I and part double I. And now part B says, state whether each of the graphs is connected, strongly connected, or not connected. So let's do A first. Connected or strongly connected? So let's take a look. Can A get to every other vertex? So A can get to B right away, which can go to D, which can go to C. So A can eventually get to B, C, or D no matter what. Can B get to A? Yes. Can B get to C? Yes, by going through D. And of course, B can get to D. C can get to A, which can get to B. And C can go directly to D. D can go to C, which goes to A, which goes to B. So every 2 pairs are connected in either direction, which means A is strongly connected. Every 2 vertices I can get from one to the other in either direction. How about double I? Well, the double I can see immediately is not strongly connected because A can't get anywhere. A can't get to B, to C, to D. Once you're at A, you're stuck. So A is so it's certainly not strongly connected. It's not unconnected because I can see edges connecting all of them. The question is it regularly connected? Well, I guess it can in theory be not connected if it's a directed graph. Maybe there's no way of getting from 2 different things. But let's see if it's connected. B can get to A, so A and B are connected. So A and B, we can go from A to B, or at least one way from A to B. C goes to A, so we have an AC connection. And D can go to A through C, so we have an AD connection. So A, there's a walk from B to A, from C to A, from D to A. Now, we have to look at BC. Can B and C ever meet? And actually, look at that. B cannot get to C because B can only get to A, which can't go anywhere. And C, oh no, C can get to B. C can go from C to D to B. So B and C are connected, and B and D are connected, and C and D are connected. So AB, AC, AD, BC, BD, CD. So we have a weakly connected or just a straight up connected graph. Okay, that was fun. I like graph theory. All right, question 3. It says for part I, for part A, part I, it says, draw an unweighted directed graph containing the information given in the following table. An unweighted directed graph. So it's an adjacency table. We have A, B, C, D, A, B, C, and D. We have 1, 1, 1, 1, 1, 1, 1, 1. An unweighted directed graph. Okay, so here's A, which can go to B and can also go to D. B can go to C. C can go to A. And C can also go to B. And C can go to D. D can go to A. And D can also go to C. Okay, so that's my unweighted directed graph. Double I. For each vertex, state the in degree and the out degree. So the in degree of A is how many edges end at A. I got 2. And the out degree at A, how many emanate from A, I also have 2. The in of B is 2, and the out of B is 1. In for C is 2, and the out for C is 3. And the in of D is 2, and the out of D is also 2. And by the way, I was getting all of that from the graph, but you can actually look at the table. Every row, remember, the tables are from 2. So A, from A, 2, that's the out of A. From B, 1, out of B. From C, 3, out of C. From D, 2, out of 2. And then into A is 2, into B is 2, into C is 2, into D is 2. So rows and columns. Okay, and then it says for part B, part I of part B, draw a weighted directed graph with the following information. So what is the information here? It's again going to be 4 vertices, A, B, C, and D, A, B, C, and D. And we have 6, 4, 6, 5, 7, 7. So what do we have here? Here's A. We have a path from A to B of 6. And a path from A to D, an edge from A to D with a weight of 4. B can go to A, also with a weight of 6. C can go to B with a weight of 5, and it can go to D with a weight of 7. And D can also go back to C with a weight of 7. So this is a directed weighted graph. And then it says for each vertex, state the in and out degree. So the in of A is nothing to do with weights. Degrees have nothing to do with weights. It's only edges. So coming into A, here we can't use a table. We got to use the graph. Coming into A, well, I guess you can. If you imagine every number in the table is a 1, then it's the same thing. So into A is 1, into B is 2, into C is 1, and into D is 2. Meanwhile, out of A is 2, out degree of B is 1, out degree of C is 2, and the out degree of D is 1. So you can still get it from the table. All right. So question number 4. It says, without drawing the graph, write down the in degree and the out degree of each vertex given in the table below. So I've already told you how to do this. If you've been following for the last couple, It's 5 vertices, A, B, C, D, E, A, B, C, D, and E. It is a directed graph. Otherwise, you wouldn't have in degrees and out degrees. As you have 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. So go ahead and find out the in and outs of each of the 5 vertices. So in A, 1, B, 2, C, 2, D, 2, E, 3, out A, 3, out B, 1, out C, 2, out D, 2, out D, 2. No explanation required if you've been following along with the examples previously. And now the last question, question 5. This is always the one that requires the most thinking. The table shows parts of the timetable for the ferries on Lake Starnberg in Germany. Again, this is an example where I'm not going to write it out because there's a lot of information there. You need it in front of you. There is a map of a lake, I guess, or something. It looks something like this. Here's Starnberg. Here's Passenhofen. Here's Tutzing. Here's Bernried. Here's Seeshalt. Here's Ambach. And here's Ammerland. I really hope this was necessary to solve this problem and I didn't just waste all my time. Anyways, so the table shows parts of the timetable for the ferries on Lake Starnberg in Germany. So it looks like there's 3 ferries. First one leaves Starnberg at 9:35, goes to Possenhofen, and then goes to Tutzing, then to Ammerland, then to Bernried, then to Ambach, then to Schiespalt, and then back to Ambach, back to Bernried, back to Ammerland, back to Tutzing, back to Possenhofen, and back to Starnberg. Okay, so it goes both directions. So part A, show the connections between the towns on a directed graph. Basically what I just did. So ST for Starnberg, P for Possenhofen, we got a arrow this way. T for Tutzing, we have an arrow this way. Then we go to Ammerland with an arrow this way. Then we go to Bernried with an arrow this way. Then to Ambach with an arrow this way. And then to Seeshalt with an arrow this way. Followed by arrow. Oops. Arrow. 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 Okay. B. State one piece of information that's easier to see on the graph than on the timetable. I don't know. What's one piece of information that's easier to see in the graph than the timetable? I don't know. What are you guys thinking there? Let's take a look what they say is their answer. It is easier to see which towns are connected and the routes between the towns. I don't know. I'm kind of looking down the timetable, and I can see very easily which ones are connected in the route between the towns. So I don't know if I agree with that one. I don't know, maybe it is. I don't know. I guess it's subjective, but it's easier to see the route. I don't know, say easier to see the route. To be honest, I don't agree, but that's what they say. Give two pairs of towns that are directly connected in one direction only. Give two pairs of towns that are directly connected in one direction only. Did I misunderstand what's going on here? It looks like they all come in pairs. What do they say? They say Starnberg and Tutzing. And Starnberg and Ammerland. What? Give two pairs of towns that are directly connected in one direction only. And their answer is Starnberg and Tutzing. I don't understand. Could be a mistake. There's lots of mistakes in these books, but I have no idea what they mean by this because Starnberg and Tutzing and Starnberg and Ammerland are connected, and they're not directly connected at all. But you can get from one to the other. I don't know what they mean there. So let's skip it. D. From your graph, give four possible routes from Starnberg to Ambach, which do not call on any towns more than once. Am I not understanding what's going on? Oh, okay. I think I understand. Okay. Okay, let's take a step back. I thought we were missing stuff in the table, but we're not. If you look at the table, not every ferry, the first ferry has lots of stops. The second ferry does not. I think that's what it means. So for example, here's Starnberg. It can go directly to Pausenhofen, which itself goes to Tutzing, which then goes to Bernried, which then goes to Seeshalt, which then goes to Ambach, which then goes to Ammerland, which then goes back to Tutzing, which then goes back to Starnberg. So that's the first ferry. The second one goes Starnberg to, I'm going to use a different color here. Goes Starnberg to Ammerland. Ammerland goes to Ambach, which goes to Seeshalt, which goes to Bernried, which goes to Tutzing, which goes to Pausenhofen, which goes to Starnberg. And the last one, Starnberg goes to Pausenhofen. Which goes to Tutzing, which goes this way to Ammerland, which goes to Ambach, which goes to Seeshalt, which goes to Bernried, which goes to Tutzing, which goes to Pausenhofen, which goes to Starnberg. Okay, so let's try this again. So those are the connections between the towns on a directed graph. B, state one piece of information easier to see on the graph than on the timetable. Well, now that I see that not every time, they don't necessarily go in order, I do agree that it's easier to see the roots on the graph because you can just follow the colors. So easier to see roots. I do agree with that now. C, give two pairs of towns that are directly connected in one direction only. So now I can see it. Tutzing goes directly to Starnberg. Tutzing goes to Starnberg, but Starnberg does not go to Tutzing. And is there another pair? Tutzing and Ambach, I do see go in both directions. So is there, what was the other one that they said was their answer for 15? They said Starnberg and Ammerland. Yeah, of course. Starnberg and Ammerland. There you go. Starnberg can go to Ammerland, but Ammerland does not go to Starnberg. Okay. Yes, now that I understand what's going on, so much easier. D, from your graph, give four possible routes from Starnberg to Ambach, which do not call on any town more than once. So Starnberg can go directly to Ammerland, which can go to Ambach. That's one route. Okay. Starnberg can go to Pausenhofen, which can go to Ammerland, which can go to Ambach. Starnberg can go to Pausenhofen, which can then go to Tutzing, which can then go to Ammerland, which can then go to Ambach, and Starnberg can go to Pausenhofen, which can go to Tutzing, which can go to Bernfried, which can go to Stiespout, which can go to Ambach. So what were their answers? Starnberg, Ammerland, Ambach, got that one. Starnberg, Pausenhofen, Tutzing, Ammerland, Ambach, got that one. Starnberg, Pausenhofen, Tutzing, Bernried, Seeshalt, Ambach, got that one. And then Starnberg, Ammerland, Tutzing, Bernried, Seeshalt, Ambach. They don't have that one, but they didn't say give all of them. They just said give four. My four are different than their four, but perfectly valid four. And then D, use the timetable. So this is a thing. The graph does not include times. So maybe some of my routes might not work because I get there too late to take the ferry. But if you're including times, use the timetable to find how many of the routes in part D could be completed in one day. So Starnberg to Ammerland, that's, okay, so Starnberg to Ammerland, I can do that. That's the 14:30 ferry. No, I lied. It's the 12 o'clock ferry. And Ammerland to Ambach, I get in at 12:44. This is a 12, so let's do this maybe a little easier. So Starnberg to Ammerland, you know what? If I do it this way, I can include it in the previous one. So D and E. Okay, different color. Starnberg, if I leave Starnberg at 12, I arrive at Ammerland at 12:44. And Ammerland to Ambach, if I leave right away, I can get there at 13:01. So that's certainly one day. If I go Starnberg to Postenhofen, I have to leave at 9:35, getting to Postenhofen at 10:07. And then Postenhofen to Ammerland, was that a route? There's no Postenhofen to Ammerland route. Uh-oh. Let's go back this one. No wonder they didn't have it in the back, because it's not valid. There is no. Try that one again. So Starnberg to Postenhofen to Tutzing. We did that one already. So yeah, it looks like there's Starnberg to Ammerland to Tutzing to Bernfried to Schiespout to Ambach. Okay. So Starnberg to Ammerland, that's 12 o'clock to 12:44. Ammerland to Tutzing, that would be I do have an Ammerland to Tutzing here. Do I not? I thought I did. Which was my red roots, my purple there? Something tells me this one, Ammerland to Tutzing. I don't see it there. What color was that one? Ammerland to Tutzing. No, it's red. Which one? Oh, on the way back. No wonder. Okay. On the way back, Ammerland to Tutzing I can do. Aha. To do Ammerland to Tutzing, this is cool stuff. To do Ammerland to Tutzing, I would need to leave here at 11:51 to get to Tutzing by 12:08. That cannot be done in one day. This one can, this one cannot. Okay. Next one. Starnberg to Postenhofen. If I leave at 9:35, I can get to Postenhofen by 10:07. So I can get to Tutzing by 10:31. Now, once I'm in Tutzing, I can wait till 15:06 and take the Tutzing to Ammerland ferry and get there by 15:22. And then I can get here to 15:39. So I can do that. And then 9:35 to 10:07 to 10:31 to Bernried at 10:49 to Schiespout at 11:08 to Ambach by 11:32. And I can do that one as well. Okay, fun problems. But I hope what this has shown you is two things. One, sometimes when you're reading a question, you don't always see exactly what they're intending, and you have to think a little bit about it. The reason why I like math so much is because I don't have to oftentimes figure out what they do, because it's usually self-evident to me. But sometimes the wording is such that it's not, and you keep at it. You try to figure out what they're talking about, and once you do, it's like, oh, I get it now, and then solving a problem can be really a lot of fun. Anyways, so that is the end of section 15.1. We will move on to section 15.2 next time, and I will see you there.